Hello, pre-calculus. We are going to start a starred section today, 6-2, matrix multiplication, inverses, and determinants. The objective for this section is to multiply matrices, find the inverse of a matrix, and find the determinant of a matrix. These will all be subject to if possible, by the way, and this is all needed for the engineer's exam for those of you who are interested in that. All right, so let me start a new board here, and we'll start in the notes. Let's talk about multiplying matrices. So there's some rules about multiplying matrices. You can't always multiply two matrices. They have to have very certain conditions, okay? And the conditions are to multiply two matrices their inner dimensions must be the same. Okay, and what that means is, suppose that we have a matrix A that is, let's say, a 4 by 2 matrix, and a matrix B that is a 2 by 3 matrix. If I was going to do matrix A times matrix B, that would be the 4 by 2 times the 2 by 3. And this I can do. It's possible. And the reason that it's possible is because those numbers are both 2s. Now, on the other hand, if I wanted to do a B times A matrix, if I wanted to multiply B times A in the other order, that would mean I was doing a 2 by 3 matrix times a 4 by 2 matrix. And because those numbers are not the same, this is not possible. So, a big note about this, let me talk about this on a new board here. Matrix multiplication is not commutative. In other words, order matters. So that's really important to us in this. The order that you multiply two matrices in actually determines whether you can multiply them at all. So the process, let's talk about how you actually do this, okay? The process for multiplying two matrices, let's say we're going to do A times B, and A is, let's say, matrix A, B, C, D. And then let's have a matrix B, which is, let's see, that's 2 by 2, so let's make this one 2 by 3. This one's 2 by 2. Let's make this one 2 by 3. So, let's see. I want to start at the end of the alphabet here, so I'll just work my way backwards. That'd be Z, Y, X, W, V, and U. There we go. And this one is a 2 by 3. So notice right away that it is possible to multiply them in the order A times B, but if we tried to do B times A, that would not be possible. Okay, so here's how the process works. We're going to do this matrix A times, and it actually turns out that that is the right way to write it this time. You can finally use that cross that I've kept you away from for so long. So times ZYX WVU. And here's how you do that. So we're going to have a 2 by 2 times a 2 by 3, which again is possible because those two numbers, the inner numbers, are the same. And it's going to turn out that our new matrix, we're going to get a new matrix with this, and our new matrix is going to be the outer numbers. So we're going to get a 2 by 3 matrix out of this. So, and the way we're going to get it is you're going to do row here, column here, and you're going to multiply and add. Okay? So let me show you how that would work. It's this one times this one. So A times Z plus this one times this one. So B times W. So that gives you this row connected with that column. And that gives you the first element. And we're going to keep getting elements that way. Then we're going to do the first row and the second column, and that's going to give us the second element for the first row. So it's going to be A times Y plus B times V. So I did A times Y, and then B times V. And then finally, that first row times the third column is going to give us the third element of the first row. So A times X plus B times U. And that's going to be the same now when we go to the second column. We're going to use, or the second row, I'm sorry. When we go to the second row, we're going to use the second row, first column, for element 2, 1. So it'd be C times W plus, oh, nope, not C times W, C times Z plus D times W. So second row, first column. And then for element 2, 2, second row, second column. So C times Y plus D times V. And then for element 2, 3, it's second row, third column. So C times X plus D times U. So that's the process of how you multiply two matrices. Let's actually look at how you would do one. Okay, so this is example 1. And let's try and multiply matrix A times matrix B. We're going to have to make sure that it's possible first. So let me tell you what the two matrices are. Matrix A is 4, -2, -1, 3. And matrix B is -1, 2, 3, -2, 4, -1. So there's our two matrices, and notice that this is a 2 by 2, and this is a 2 by 3. And so if we multiply them in that order, it is possible. So we can do A times B. Notice that we could not do B times A. I'd like to put a little side note here, but I'll just put it like this. B times A, not possible, because we'd be doing a 2 by 3 times a 2 by 2, and then the inner numbers would not be the same. So we can't do that, because you have to be able to multiply every element by something and add them all together between the two, and so that's why we need those inner numbers to be the same. So A times B will give us a new matrix. It will be a 2 by 3 matrix, and the way I'm getting that is the 2 from here, the 3 from there. Tell me that it's going to be a 2 by 3 matrix. Okay? So again, it's going to be first row. I'm going to use the first row of A and every column of B to do that with. So first row, first column, element 1, 1 is going to be 4 times -1 plus -2 times -2. And that's how I'm going to get that that element 1, 1. Okay? And then same thing with the second column here. For element 1, 2, I'll do 4 times 2 plus -2 times 4. And then finally, the first row of A times the third column of B will give me element 1, 3. That will be 4 times 3 plus -2 times -1. So there's the elements of that one. I'm going to switch colors here. I'll use blue here for the second row. And then I want to do the same thing for these, and I'll just use this color for these. So we're going to have for element 2, 1, -1 times -1 plus 3 times -2. And then element 2, 2, -1 times 2 plus 3 times 4. And then for element 2, 3, second row times the third column, -1 times 3 plus 3 times -1. So that will give us what we need for our matrix, and then we can start putting everything together. 4 times -1 is -4, plus -2 times -2 is 4. 4 times 2 is 8, plus -2 times 4 is -8. 4 times 3 is 12, plus -2 times -1 is +2. And then -1 times -1 is +1, plus 3 times -2 is -6. And -1 times 2 is -2, plus 3 times 4 is 12, and -1 times 3 is -3, plus 3 times -1 is -3. And so I get a final answer of 0, 0, 14, -5, 10, and -6. So there's my final matrix. So that is matrix multiplication. Let's then talk about a different idea, which is an inverse matrix. And the way an inverse matrix works is that if you have, let's say you're doing it with 2 by 2s, which is going to be the only inverses that we have right now. We're going to have to talk about determinants also, but the way an inverse matrix works is that if you have, let's say, a matrix A, which is a 2 by 2, then A inverse is a 2 by 2 such that A times A inverse will equal 1, 0, 0, 1, like that. And that will also be the same if you do A inverse times A. Inverses can only be found for square matrices. So that is a 2 by 2, a 3 by 3, a 4 by 4, and so on and so on. You can't find an inverse matrix unless that happens. It also turns out that a matrix only has an inverse if the determinant of the matrix is not 0. So then we have to talk about how to find the determinant. Okay, and again, we're only going to talk about this for 2 by 2 matrices. We're not going to bother with larger ones because as they get larger, they get a lot more complicated. So determinant of a 2 by 2 matrix. And we'll go through this as well, okay? To find the determinant of A, that's the notation right there. To find the determinant of A for, let's say we've got matrix A, which I'll just call A, B, C, D again. The determinant of A, which has the notation A, B, C, D in these, they look like absolute value bars, and in fact they're actually really close to absolute value bars in what they mean, but from a matrix sense, is to multiply the diagonals, okay, and subtract them. So you do A times D minus B times C, and that is how you find the determinant of something. So we're going to put all of this together. One more note, though. 2 matrices, A and B, A and B are inverses if and only if, remember that's the notation for if and only if, A times B equals 1, 0, 0, 1, as well as B times A. Okay, so part of what we're going to do, and we're going to do this in the first example, is determine whether 2 things are inverses. So this is example 2, and the question is, are A and B inverses? And where matrix A is the matrix 7, -4, -5, 3, and matrix B is the matrix 3, 4, 5, and 7. So they would be inverses if we do, so these are inverses if and only if A times B is that matrix 1, 0, 0, 1. So that's what we're going to test. We're just going to multiply them together, and it is true, it is a fact that if A times B equals that identity matrix, by the way, they call this the identity matrix with a capital I, If A times B equals that identity matrix, then B times A will also. So I'm only going to check them in one order. You're really technically supposed to check them in both, but I'm going to skip that part. So A times B, first row, first column, that's 7 times 3 plus -4 times 5. First row, second column is 7 times 4 plus -4 times 7. And then second column, or second row, first column, is -5 times 3 plus 3 times 5. And then second row, second column, is -5 times 4 plus 3 times 7. So let's figure out what all that is. 7 times 3 is 21, plus -4 times 5 is -20. 7 times 4 is 28, plus -4 times 7 is -28. -5 times 3 is -15, plus 3 times 5 is 15. -5 times 4 is -20, and 3 times 7 is 21. And so we get 1, 0, 0, 1 as our multiplication, as our product of the multiplication of those two matrices. So the answer is then yes, A and B are inverses. So one more set of notes here. To find the inverse of a 2 by 2 matrix. And let's call it matrix A. Okay. A inverse, and that's the notation there, A inverse is equal to 1 over the determinant of A times, and let's say A is that same A, B, C, D matrix. So to find the inverse, it's 1 over the determinant of A times a new matrix where you switch those diagonals, so A becomes D and D becomes A, switch those two right there, and then you keep these diagonals but you make them the opposite sign. So keep these two but make them the opposite sign. Note that A inverse only exists if the determinant of A does not equal 0. And that's not just true for 2 by 2 matrices. That is true in general. So as a real quick check as to whether or not a matrix has an inverse, you can just take its determinant, and as long as it's something other than 0, anything other than 0, its inverse exists. So let's do our last example here, example 3, we are going to find the determinant of a matrix A that I'm going to give you. A is going to be the matrix 2, -2, 3, -6. Then find A inverse if it exists. Okay? So the first thing that we got to do is find the determinant of A. So that, another way of writing that is to put the matrix inside of these absolute value bars. And I'm going to do the diagonals multiplied together. So 2 times -6, and then subtract between them. And -2 times 3, which is -12 minus -6, which is -12, plus 6, which is -6. So A inverse exists because the determinant of A does not equal 0. It equals something other than 0. So I know that the inverse exists, so now I can work on finding it. So let me write down our matrix one more time. 2, -2, 3, -6, and I'm going to make a note here that the determinant turned out to be determinant of A equals -6 because I'm going to need that. And then A inverse is equal to 1 over the determinant of A multiplied by, and this is going to be a scalar multiplication, we've done that before, multiplied by a new matrix, this modified A matrix, where I'm going to switch those two. So it's going to be -6 here and 2 there, the new diagonals there. And then I'm going to take these two and I'm going to make them opposite signs. So this is going to be +2, this is going to be -3, and then I'm just going to do that. So that's going to be A inverse equals 1 over -6 times -6 times 2 times, or -6, 2, -3, 2, and I'm going to multiply that -1/6 excuse me, times each of those elements. I'm going to distribute it as we've done before. So -1/6 times -6 is 1. -1/6 times 2 is 2 over 6, which reduces to 1 over 3. -1/6 times -3, oh, that's -1/3, sorry. -1/6 times -3 is a +3 over 6, which reduces to a +1 over 2. And then -1/6 times 2 is -2 over 6, which is again -1 over 3 when we reduce it. So this then is A inverse. Those are the notes for section 6.2. Section 6.2 is a starred section, remember, so it's an important section for us. And I hope those notes were clear, and I will see you next time. Thank you.